Okay, hi everybody, my name is Andrea Corallo, and this presentation is about the Emacs Lisp native compiler. So having GNU Emacs able to compile and run Emacs Lisp as native code. This project has been my hobby project for the last about 2.5 years, and we will see a little bit where this project is coming from, where we are, and where we want to go. So essentially everything you need to know about Emacs Lisp native compiler, and probably a little more. So just a little bit of context on Emacs Lisp. Emacs Lisp is a programming language. It's indeed a Lisp. And 1 year ago, I've looked for some statistics, and I was kind of pleased to see that, I was surprised to see actually that it's still kind of popular as a programming language. It doesn't rank that bad against other programs. Also, the other important fact about Emacs Lisp is that there is a lot of Emacs Lisp out there, and this will have an impact on this project. It's a programming language that is capable of almost any task, so it's almost a general purpose programming language. And this reflects on Emacs itself, that it's capable of almost any task. Indeed, this almost is something that we want to fix, because we want to do everything we want, all of our computing with it. Also, an interesting aspect, at least for me, is that it's not specified by any standard. This implies that it can evolve in a more agile way without having to change the standard, and etc. And in fact, it's kind of improving, I believe, relatively fast. A little bit about Lisp in general. Well, first, it's the best programming language ever. We all know it. It has a lot of very nice properties, like it's dynamic, it's iconic, etc. But the interesting thing for implementers is that, in theory, it can be implemented with very few primitives. So you build very few primitives that are like magic. And on top of this, you can implement a whole language. This sounds very nice and very appealing for implementers willing to implement a new Lisp implementation or improving and modifying an existing one. So the question is, how many primitives do we have to re-implement if we want to change the GNU Emacs Lisp implementation? Well, unfortunately, it's not really these are not that few as we would like. Yes, so in GNU Emacs we have about 1,500 primitives. And the main reason for that is performance. So actually, GNU Emacs was written when performance was a big issue. And still nowadays, certain parts are still performance critical. So we have a lot of C code. Actually, 30% of the GNU Emacs code base is C code. And we have to maintain this. But not only, this is the main barrier for people that tried in the past to change the Emacs Lisp implementation, because not only you have to replace these primitives, all of them or part of them, but sometimes they do also share these primitives internal data structure. So for instance, it's very difficult to say, okay, now I want to go from C to a different programming language for implementing these primitives. So this has been effectively the main barrier for solving this problem. Other interesting aspect about the GNU Emacs implementation is that Lisp can run interpreted or byte compiled for performance. And the byte compiler itself is written in Emacs Lisp. This implies that GNU Emacs has to go through a bootstrap procedure in order to be built. But it's kind of interesting for something that was that started as a text editor or something like. Yes, the bytecode, that is the Emacs Lisp when it has been byte compiled, it's running a stack-based virtual machine that is implemented in C. Okay, so I've listed a bunch of areas where Emacs Lisp could improve. Namespace, extensibility, performance, and debuggability and diagnostic, we could say. This activity, this project in particular, is affecting primarily performance, and in the performance area, the execution engine. That said, I think it has an impact also on extensibility, and I hope it will have an impact also on programming diagnostics, so giving better warnings. We'll see more. Okay, so which are the benefits of increasing the Emacs Lisp performance? Well, indeed, we will have, if we do that, programs that run faster. But the main implication of that is that we could write less C, we could maintain and debug less C, that it's kind of a time-consuming task. And we could also allow for writing performance critical extensions directly in Lisp without having to use systems like him. I think there's a bunch of, I mean, these are very consistent benefits. Okay, project goals. But I think the title of this slide maybe should be project requirements. So when I started this activity, I set some requirements to the project with the main goal in mind to go upstream. So I wanted to create something, a modified implementation of GNU Emacs that was compatible as close as to 100% as possible to the current implementation. And when I say current implementation, I don't refer to what the Emacs Lisp programming manual is specifying as expected behavior of the implementation, but really the implementation itself. This is because there are a lot of corner cases that are not specified by the manual, but programs do rely on that. And given there is a ton of Emacs Lisp already around, compatibility was definitely a major requirement. I wanted to produce something that had reduced the impact on the Emacs code base, at least as much as possible. So I didn't want to rewrite all of GNU Emacs. Well, indeed, because it would have been too much work for one single person, but also, yes, still thinking to an upstream outcome, all of this. Another requirement was to have no or very reduced impact on the user. So I didn't want to change the way Emacs is used by you. And last but not least, introducing new dependencies. Those dependencies had to be free software, possibly GPL. And also another important requirement is that these dependencies had to be some kind of trusty software that we know is going to be maintained in the future. Even Emacs, it's around since forever and will be around forever and ever. This was another very important point. Okay, a little bit of history of this project, say a quick timeline. So 2019, in May, I did my first commit. I think it was like when I tried to write my first primitive function ever in C within GNU Emacs. And this was an attempt to try to compile, I believe, a function that was once executed, returning like 3. That was it. 6 months after about, I had something that was kind of workish. So I was able to start up a semi-standard Emacs and then to compile and load and replacing most of the functions that I had defined and floating within my Lisp unit. Those functions are the functions that are essentially composing Emacs, at least the Lisp side of Emacs. A lot of features were missing, like I had no garbage collector support, no bootstrap. I was not optimizing these functions because optimization were a little broken, no image dump support, etc. But I think this proved that the design could work. So I sent an email to Emacs Devel and said, I have this stuff I'm working on, and I wanted to get some feedback from the upstream to see if there was some interest. I believe the outcome of this was positive because about 1 month after, I pushed my branch within the Emacs Git as a feature branch. And shortly after, we started to use also the bug tracker to track bugs. So essentially, we moved the development on the upstream infrastructure. I believe 2 years after the first commit, the project was merged. After literally hundreds of bugs solved and improvements, suggestion and work. And this was about 6 months. Okay, so before discussing how the native compiler is working, I think it's worth of looking at how Lisp is implemented in GNU Emacs. So Lisp, we have Lisp objects that are floating around our Lisp universe, and they are internally represented in this way. So we have what is called a tagged pointer, that is just a regular pointer, that is pointing to the area of memory where we hold the real data of the object. But within this tagged pointer, we reserve a few bits to indicate the type of object we are pointing to. This is important because each time we access an object, we have to typically check those bits to check that the object we are manipulating is of the right kind. Remove those bits, and if we are happy, access to the object, otherwise. all the objects are like this, except for typically fixed nums that are a small integer that we manage to fit directly within the. Also, for manipulating fixed num, we have to check the tag bits each time. Whenever we are not sure about the type of object we are manipulating, read almost every time, we have to check those bits and remove those bits before doing any manipulation of the fixed num. Okay, so how Emacs Lisp byte compiled and executed in a, let's call it vanilla. So if we have a Lisp expression of this kind, so we take the variable a, we do +2, and then we multiply the result by 3. The byte compiler will produce this lat code. Lat code is essentially the assembly for the bytecode. So it's the intermediate representation, if we want, that will be assembled into byte.tlc file. How this program is executed? Well, as I mentioned, it's executed in a virtual machine that is stack-based. So we start with an execution stack that is empty and a stack pointer that is pointing to its bottom. Then we execute the first instruction that is loading within the stack, pushing in the stack the value of a, in this case 100. Then we push the constant 2. Then we do the summation and we have the result in the stack. Same, we push the constant 3, we do the multiplication, and we will be able to return. Now, what's good and what's bad about this? The good thing is that it's very simple to start from Lisp and compile this kind of output. At least very simple. It's reasonably simple, so the compiler is not that complex. The bad thing is that all this machinery, push and pop, etc., it's very different from how a modern CPU is working. Because modern CPU, they are not anymore stack-based, but they have instead a fixed number of registers, and they work with assignment and operation within these registers that are generally called general purpose. So to execute this program, this lab program, there is another program that is the implementation of the VM itself that is essentially doing a conversion during the runtime. So it's interpreting the lab program and it's converting it in instructions that we can execute in the CPU. This conversion is done each time we will run some bytecode. And it's something that we want to avoid. Instead of this live conversion, we want to convert once our Lisp program in native code. That is a binary program that can be executed directly by our CPU. So we want to save all this unnecessary conversion that we do each time we are running a program while we are running. And we want to do this process just once when we are compiling. That's the main goal of this activity. Okay, so how the byte compiler is implemented? Well, as every compiler, it's a pipeline of transformations. We go through macro expansion, closure conversion. We have a bunch of source level optimization. Then we go into lap. That is the important transformation we are interested in. And after a few optimizations on lap is assembled into bytecode. So if we reason in terms of intermediate representations, we can simplify this pipeline like this. So we start with Lisp. At a certain point, we are manipulating the program in lab form, and then at the end we produce the bytecode that is the TLC file. So what I wanted to realize was something like this. I wanted to start from lab, do something, and jump into GCC using libgcgit, and in particular the libgcgit intermediate representation that we will discuss. Now, why I wanted to do something like this? Well, essentially, writing a compiler from scratch for Emacs Lisp would have been a very big task. So I wanted to rely on, as much as I could, on the Emacs Lisp byte compiler, because I had to produce something that was as much as compatible as possible to the current implementation. So this was, like, I believe, a very good idea to save an enormous quantity of work and to produce something that was compatible in terms of semantic with the original implementation. Also, I didn't want to implement a code generator for each architecture we were targeting. I didn't want to implement all these optimizations that are already in GCC. So I thought it was a good idea to rely on an existing compiler like GCC, let's say. Okay, so let's talk about libgcgit. It was added by David Malcolm in GCC 5. It allows you to describe a C-ish semantic to GCC and to have it compiled. And it's good for building jitters or head-of-time compiler. And if we talk about GCC, well, GCC, it's a compiler. It's a very good one. It has support for a remarkable number of target architectures. It's also very good in generating fast code. And well, it's around since a long time. I believe it's like 1 year younger than Emacs. It's still very well maintained, and we can assume it will be maintained for quite a while. And as I mentioned, this was a very important point. Also, it's GPL, it's free software, and it's developed under the GNU umbrella. So I thought it was a very good option. So we can imagine a simple translation that goes from LAP to this subset of C that we can describe to libgcc. Well, this simple translation, the simple translation we can see here, it's actually pretty trivial. So instead of doing operations within the execution stack that we have seen before, we have just an array that is replacing it, and it's called local in this case. And we have assignments within these arrays that are done in place of the original push and pop activity of the stack. The nice thing is that when you have done this translation, GCC will be able to optimize this and remove all the unnecessary operation and generate code for the specific CPU you are targeting, that is running your. This sounds great. It sounds like a very simple and effective translation. And in fact, the first iteration of my compiler was doing just this. There was like essentially a big C function that was taking LAP and was doing this conversion, describing the output to libgcc. Unfortunately, if you do this, you will discover that you have like a performance upper bound limit of about 3x. So yeah, it was an option, but I thought it was like a good occasion for trying to do something more. And doing something more, it means implementing a smarter compiler that is doing some advanced analysis on the code and will be able to perform Lisp-specific optimization. So optimizations that takes advantage of the specific Lisp semantic, something GCC is not aware of. And while I was thinking about that, I thought that having a smarter compiler had also other advantages, like a smarter compiler that is understanding the semantic of the programming language that is being compiled would be also capable of giving feedbacks to the programmers, like better warnings and errors. So I was like really fascinated about this idea. And I wanted to change my implementation because I was not really happy about it. I had a lot of C code in terms of lines that was not doing any smart job. And I wanted to move write all the interesting logic in. So yeah, optimizing outside GCC actually before jumping into GCC, as I mentioned, has two main targets. Either optimize the code before going into GCC, or either presenting to GCC some code that we know GCC can optimize effect. And also, this would give, as I mentioned, better option for the compiler to provide warnings, errors, better diagnostic. So this is pretty much what the native compiler looks like nowadays in terms of passes. So we have a list of passes, each of one, it's taking an input and producing an output. So it's doing either an analysis on the program that is being passed, or either it's performing a transformation. All of these passes are implemented in Lisp, and only the last pass is implemented in C, and is the one that is, let's say, talking with libgcc. To do that, I have introduced a new intermediate representation that I called Limpol as a tribute to GCC Gimbal. That is the main internal representation of GCC. This is one of the main. So introducing a new intermediate representation, so a new way of representing my program, solved a bunch of problems. First, it allowed me for implementing, we can say, non-trivial analysis and transformations, the one I needed in my compiler pipeline. But also, it solved the problem of what was the boundary between what I had to implement in Lisp and what in C. Because once I had my intermediate representation defined, essentially the boundary between Lisp and C is just a function that is the one that is implementing the final pass. That is taking as an input all my programs in limp representation, and it's doing his bit. So I was convinced this design at least had sense. So we will go through some of these passes just to give you an idea of what these are doing. So the first pass is just responsible for spilling the lap from the byte compiler that effectively here we are using as a front end for our compiler pipeline. The second pass, called limpify, will be in charge of converting lap into limpol. So limpol is, as I mentioned, intermediate representation that is control flow graph based and is capable of SSA. So we can have a look to what this means. Let's assume we have our lab program. As every program, that's a simple list of instructions that we will execute one after the other. Some of these instructions are special instructions that we call conditional branches, where we check for a condition, and if this is verified, we are jumping to a different address within the program. Addresses that here we are calling labels. So we can split our program in chunks, and those chunks are the chunks of the program that we execute without interruption. So we always enter from the top of those and we exit from the bottom. We can name those and split them apart. And these are what we call basic blocks. And now we have a bunch of these basic blocks that are floating and are not anymore sorted. This is what is called a control flow graph based representation. And now we can get into the SSA topic that stands for static single assignment. So I don't want to get into the details, but just to give you a feeling, I added into our basic blocks in our control flow graph few assignments. We will transform this into SSA just for the variable x, just for the sake of demonstrating it. So essentially this is done through a number of phases that are essentially some analysis and mainly renaming. But the outcome, that is the one that we see here, looks quite similar to the original one. But we can see that the variable x has been renamed, and now we don't have anymore just one, but a number of this variable. The interesting property is that each one of these variables is assigned just once. And this allows for the compiler to do prediction of what is going to be the value of that variable, depending on the position within the control flow graph. This is very important. For instance, a very simple case is x1 that we see it's assigned once by definition, and in particular here at the beginning. While here it's very simple to understand that x1 will have the value 3. While for instance it's more difficult to prove what is going to be the value of x5 because it's calling a function and we don't know at the moment what x4 is. So yeah, the compiler will gain the capability to do prediction on all the variables, and the more we get information on one variable, the more we can prove about others. Okay, coming back to our passes, the next one is forward propagation. This pass is responsible for doing what I briefly mentioned just before, that is doing proof over all the different variables in the different positions of the control flow graph about their values, types, or ranges. This pass is also responsible for executing functions when we know that a function has no side effect and the pass managed to prove all the values of its argument. So the function is executed in the compile time and doesn't exist even anymore in the produced code. Then we have another pass. This is an example of a pass that is very Lisp specific. So it's trying to remove the call to funcall when those are not necessary. So there is a couple of situations where this is very useful. And not only this is beneficial because we are generating better code, but when we manage to do that, we allow also GCC for better analysis over the code because GCC knows nothing about funcall. So if we are calling from foo directly bar, well, for GCC it's way easier to do its analysis on top of this code. Another interesting pass we can mention is TCO. This is performing tail recursion elimination, so it's essentially allowing for a more functional programming style if you want. We can jump to the last pass that is called final, and as I mentioned, this one is responsible for taking our program in limp representation and describing it to libgcgit in libgcgit IR. So that's the main task. It's also defining inline functions for accessing fundamental data types and so on. This pass, it's also responsible for using some of the predictions that has been done by the previous passes to generate better code. Okay, so things we had to add in order to have all of this machinery to work and to be controllable. The first one is a knob. It's called native comp speed, and it's the equivalent of the common Lisp speed. It represents the optimization level. The default is 2 and is the maximum optimization level that it's meant to reflect all the original semantic of the Emacs Lisp. So it's the one that should be used by default. The second one is compilation unit, and it's a kind of new object that has been added to Emacs. Let's have a look to how the garbage collector works in this case. The GNU Emacs garbage collector, it's a simple mark and sweep garbage collector. So essentially it does a tree walk through all the objects and is following references from one object to the other. All the objects that are reachable during a mark phase will be kept in our Lisp universe. All the other one will be freed. So in this case we have a bunch of functions, foo1, foo2, bar1, etc. that are defined. When a function is defined, it is accessible through its symbol. So we have the symbol that is referring to the function. And the function, in this case it's a native compiled function, is referring to the compilation unit. The compilation unit is essentially the ELF file that has been compiled, and it's containing all those functions that came from the original .el file and that we have loaded into memory. Indeed, if for instance, bar1 and bar2 are undefined, functions 2 and 4 will be not anymore reachable, and we will be able to free them and download the compilation unit. So we discussed quite a lot about control flow graph, SSA, and a lot of boring stuff, and I promised you that we are doing a lot of interesting proofs over variable. So let's have some example of them. Let's jump into a quick demo to see what all of this abstract theory and this exoteric propagation engine can do for us and how the user can interact with it. So I have a file with a bunch of functions and I will native compile and load it. Alright, Emacs is native compile and load. At this point I can disassemble foo1 just to make sure it's native code and I'm not lying. So these are the instructions that would be executed directly by my CPU when I call this function. Alright, very cool. Now, symbol function of foo1. Interestingly, this is returning a subroutine, as it would be a primitive function, because this is native code, even if it's written in Lisp, has been converted to native code as it's a primitive function. But we can do also a new thing, that is asking for the type of the subroutine. Alright, very cool. It says this is a function, it's taking one argument of type t, that means anything because we don't have any information, and it's returning a type t. So also there we don't have much information. Okay, very cool, but not very useful. Let's see foo2. Alright, foo2 is slightly different. It doesn't take any argument, but it's returning an integer included between free and free. Wow, amazing. Okay, let's get into something a little bit more complex. Foo3. Foo3, it's taking one argument we know nothing about, but it's returning a number. And why it's returning a number? Well, essentially because 1 plus it's returning a number. And if in all the other cases it would signal an error if it's not happy about its input argument. Let's have a look to foo4. Okay, so foo4 it's a little bit more complex. It can return nil if the when condition is not satisfied, so it's type null, nil. It can return a floating point. We don't do any propagation on floating points so far. Or it can return an integer included between 4 and 9. Wow. Let's go on with foo5. Okay. So foo5, it's even more complex because other than having to satisfy this condition, we can see that the result of the propagation of this complex condition is propagated also across the plus. So this foo5, it can return nil, a floating point we know nothing about, or an integer included between 12 and 24. Let's go on with foo6. Okay, foo6, it's returning anything but an integer. Well, I think it should be pretty obvious why, because if it's not an integer, we return it, otherwise we signal an error. Let's finish with foo7 very quickly. Okay, so in foo7 we have another very complex condition, at least for me, but it's interesting to see that we are also propagating values for symbols. So we can return a symbol, the symbol big, the symbol small, or an integer included between -100 and +100. Now the question is, why all of this is useful other than having Andrea very happy when he's playing with this all the day? Well, we have to come back 1 second to how Lisp objects are represented within Emacs. As I mentioned, Lisp objects are represented as essentially machine words, where we reserve a few bits to indicate the type. And every time we are accessing the object, when this is a fixed num or a regular object where this is a pointer, we have always to extract these bits, make sure that they satisfy a condition. So we make sure that we are going to manipulate the object of the type we expect. And then we can really extract the object and do the manipulation. If the compiler managed to prove that the contained object is already of the right type, it will be able not to emit the type check and save a lot of instructions. This is a very powerful optimization. So let's discuss some potential future development in this area. First, I think it would be extremely nice to extend the propagation to types that are not built in. There are a lot of cases where we could optimize effectively, like for instance, when we do a lot of accesses to structure slots or stuff like that, where we keep on checking and checking the same object for the type, where it's obvious, well, it should be trivial to prove that it's the right type after the first access or things like that. So I believe this is a low-hanging fruit in terms of performance. Also, I think it would be really nice to extend the declaring mechanism in order to allow the user to declare argument types optionally, indeed optionally. Doing that would give the compiler a lot of information to propagate value types within the function, but also would allow the compiler to give to the user really good diagnostic during compile time. Like the compiler could say, hey, here you are calling a function that is expecting this argument to be of this type, but I'm proving that you are calling it with an argument that is of this type and is not a subtype of the expected one. So you're doing something not coherent. So this kind of interprocedural logic. And I think the compiler should also take advantage under certain circumstances of this interprocedural analysis in order to optimize even more when possible. Also, I think we should work on our backend to improve the code generation depending on the prediction that the compiler is doing. We already take advantage of those predictions, but I think we could do better. We can have a quick look to some performance results. So these are the results from the eLisp benchmark package within GNU-ELPA. So this is the performance uplift, and we can identify pretty much four classes of results. So the first one is the one where there's no performance uplift because there is not much we can do, and the time is probably not spent within the execution engine. And the one around the 3x are the one where probably we are not triggering many Lisp-specific optimizations, but just the fact that we are converting into native code, it's giving us this performance uplift. Then there is a bunch of other benchmarks where the Lisp optimizations are triggering in, and yes, and the uplift is way bigger. And then we have 3 benchmarks that at the time are completely optimized out. That means that the compiler became so smart that was able to compute the result in the compile time and just put the result in the generated binary. Okay, so let's discuss a little bit the compilation model. This is an hybrid one. It's both JIT-like and ahead-of-time-like. So Emacs is composed by what? By what we call an Emacs image. This is essentially the Emacs binary that we start. It's including all the C code plus all the Lisp code that we preload. Then we have all the rest of the Emacs Lisp code base that can be loaded just if it's required. Same for the external packages if we have any. If we build an Emacs Lisp with native compilation enabled, by default, only the Emacs image will be native compiled. All the other code will be compiled on the fly when it's loaded and executed the first time if it's necessary. Same for the packages, in a transparent way and asynchronous way. Also worth noting that the result of this compilation will be stored into a cache directory within the home directory of the user. So it will be able to, it will be reused in the following sessions if the same file is loaded, without having to recompile multiple times the same file in different sessions. So it works a little bit like that. When we load the bytecode for the first time, we spawn a native compilation process. In the meanwhile, we keep on using the bytecode that it's available. When the native compilation is finished, we hot swap the definition of the functions that are contained into the file, and we start using the native code in a transparent way. We do this asynchronously and for more compilation units at the same time, so it looks a little bit like this. Okay, so let's try a quick demo of all of this machinery. I've started a fresh Emacs with native compilation support, and at this moment nothing is going on, as you can see. Now we will test the machinery with Tetris because I can't imagine anything better to test this. All right, so what I do expect is that when I launch Tetris, it will be loaded. It will immediately start the execution of the byte compiled version, so we will not see any delay in the user experience. And in the meanwhile, a parallel process will start to native compile Tetris itself. When the native compilation will be finished, the function of all Tetris will be hot swapped, so we will not see any interruption. Okay, so Emacs Tetris started and it's running. We have seen no delay, and in the meanwhile, the native compilation is probably already finished. We can have a look within this async native compilation log buffer. So we see that Tetris has been native compiled and all of its dependencies. Now, Tetris is still running, but I can do Ctrl+F. Tetris, okay. And we can see that Tetris is an interactive native compiled Lisp function, so it has been native compiled. I can even disassemble if I want. Okay, so very cool. I guess we can say this mechanism is working. Also, worth noting that if I get back to the async native compile log buffer, we can see that we have compiled another bunch of files. Essentially, I think these are because of my Ctrl+H+F describe function command and disassemble and so on. So the first times you will run Emacs, you will have from time to time these processes that are spawned. So Emacs is like compiling itself and it's replacing the bytecode definition with the native one. But after a few sessions, you will not see this anymore because the output of this compilation, as I mentioned, are stored in the user directory. All right, so to conclude, Emacs with native compilation support is coming up in Emacs 28. That is going to be the next major stable release that will be released. So we have all to celebrate with a big party, I believe. But before going to the party, I'd like to list a few points that I think had been like success factor in this in upstreaming this work. So it's been extremely important to get in touch with the upstream as soon as possible, as soon as I had proof of concept. It's been extremely important to involve the community as much as possible, and this included like keeping a development blog and post about that on Emacs Devel, and also producing material, participating to conferences and giving presentations like the one I'm doing to explain what I was doing and how it works. Has been extremely important also to be able to rely on the upstream infrastructure, so to develop the software as a feature branch in the official Git, but even more I would say to use the official bug tracker for solving bugs of this branch. This gave the opportunity to stay really in close touch with maintainers and senior developers of Emacs that helped me a lot, and at the same time they were informed about what I was doing and what was the status of this feature branch. Extremely important. And also I think played a major role to try to design this enormous patch in a way that the impact on the current code base was minimized, and also, well, at least as much as possible, and also minimizing the impact on the user operation of the software, in this case Emacs. So yes, mandatory special thanks, well, Emacs developers, and especially maintainers and senior developers like Stéphane Monnier that helped me a lot across this long journey. And well, all the community that really got so excited about this project and gave me the energy to go through all of this time and development and bug solving, etc., etc. So yes, it was a really exciting time, and I think we have to look forward and start thinking about how to improve all of this for the following years. And that's it. I think I should be online for questions. Thank you very much.